we discussed about four-noded quad element, and we also concluded that to evaluate its stiffness matrix, we probably have to use some numerical method, and getting a closed form integration would probably not be possible most of the times. Now, now we could straight away go for discussing such numerical methods, but it would be helpful if we could look for other elements, and how uh, the numerical methods could also be important for them. So let us now construct our Pascal's triangle. So as we discussed earlier, the Pascal's triangle becomes a Pascal's pyramid when you go for three-dimensional elements. So there is xi, there is zeta, and up to this is these are the constituents of the shape functions of a CST element. Now, if I move for the quadratic terms, okay. So up to this, as we discussed, you have the CST, and then by taking these four terms, we can form the four-noded quad elements. Next, these are the terms. And then next there are such terms. I hope you can see or identify these terms. Let's say if you do binomial expansion of xi plus eta cube, you would see such terms. So these are the all possible cubic terms involving xi and eta. Now let's go for to the power 4. Okay. Okay. Now, if I take up to this level, these are the different terms for required for constructing the shape functions. You can see six terms, and it forms a triangle. So it is for six-noded triangle. Okay. So let us construct the six-noded triangle. This is the arbitrary triangle in the physical coordinates, and let's say these are the corner nodes, and after that you would be having the mid-side nodes, so I can number them as 4, 5, and 6. In the natural coordinate, this is how the triangle looks like, a right angle triangle. So coordinate of this point is 1, 0, and this is the origin, so 0, 0, and this one is 0, 1. And if I number the nodes, so this one is the node number 1, this is node number 2, and this is node number 3. So up to this we have seen with CST element. So between 1 and 2 then comes exactly in the middle 4. So the coordinate of that point should be 0 0.5, 0 0.5. Then between 2 and 3 comes your node number 5, and between 3 and 1 comes your node number 6. Can you tell me what is the coordinate of node number 5 in natural coordinates?
0,5.
0.5. And what about 6?
0.5.
0, right? Okay. So again, you can imagine each of these each shift function in this case would be quadratic, and it would be having terms of xi square, eta square, or xi eta up to this. Okay, so another rule that has to be satisfied is that the ith shift function with at jth node should be Kronecker delta, which is that is equals 1 if I equals j and 0 otherwise. Okay, and summation of all the shift functions must be equal to 1. So these are the two rules of constructing shift functions. So now let us look at shift function 1. That is supposed to be unity at node number 1 over here, okay, and 0 everywhere. Now if I look at all the nodes uh, that are not node number 1, so all the nodes except node number 1, they mainly remain on these two straight lines. Can you see this? The line 2 3, it houses node number 2, node number 5, and node number 3, and line 4 6 houses node number 4 and node number 6. Okay, can you
Yes,
tell
sir.
me what is the can you see this?
Yes, sir.
Yes,
Okay,
sir.
so can you tell me what is the equation of node number sorry, this line housing 2 3 5? What is the equation of that line?
Y equal to 0.
Xi equal 0.
Sir,
Hmm,
xi
equal
equals
to 0.
xi equals 0.
Y equal to 0.
So xi minus 0 is a coefficient. What is the equation of the line 4 6?
xi equals to
Y
0.5.
equal to 0.5.
Okay, so in other words, I can actually write the equation to be twice xi minus 1. Okay, that also is the equation of this line. Okay, now that means for each point and even these nodes lying on this line 4 6 would be 0 because this part is 0, and each point including these nodes on this line will have a value of will give you a value of 0 for n1 because this term becomes 0. Now substitute for the value of xi and eta, or the coordinates at node number 1. What value do you get for n1?
Sir, 1.
1. So that means no scaling is required, so we can write it like this. Okay, so can you construct all the other shift functions? For example, let's try node number 4. So we tried one corner node. Can you try one of the mid side nodes? So if I do n4, so that is going to be 0. That is going to be 0 on the line 2 3 and 3 1. So every node other than node 4 is housed in these two lines, line 2 3 and 3 1. So what is the equation of the line 2 3?
Eta into xi. Eta xi.
No, what is the equation of the line 2 3?
Sir, xi plus eta equals 1.
Xi is equal to 0.
Xi minus 0. Okay, and equation of line 3 1 is eta minus 0, right?
Yes,
Eta
sir.
minus 0 equals 0. Okay, or eta equals 0. So the expression for n4 is xi eta. Now if you substitute the coordinates of node number 4, what value do you get for n4?
1 by
1
4.
by 4.
1 by 4. So that means it needs to be scaled by 4. Okay, then if you substitute the values of the values of xi and eta at 4, then you would get n4 equals 1, and therefore would be satisfying this condition. Okay, and we would try to construct each of these shape functions by taking minimum number of such lines, such straight lines. Okay, if we ensure that, then this would automatically be satisfied. Okay, this should automatically be satisfied everywhere within the geometry. That is what's supposed to happen, that whatever the expressions of ni's are, if you sum them up, the net value is going to be 1. So can you construct all the other shape functions? For example, can you tell me how much is n2? Or n3? N3 is going to be interesting because for N3 you are supposed to take the line 5, 6 and line 1, 2. So you'd see that each shape function has some term from their CST counterpart. Okay, so now can you tell me what is the expression for N5?
স্যার n3 টা কি করে হলো, মানে 4 6 এ 0 হচ্ছে আর 1 তে আর 2 2 5
No,
এ
you're supposed to take these two straight lines. The one that is housing 1, 4 and 2, okay, and the other one that is housing 5 and 6.
okay.
Okay, so what is the equation of this line? 1 minus xi minus eta equals 0, right? And what is the equation of this line? 0.5 minus xi minus eta equals 0. তোমাদের সেমিস্টার কবে রিজলভ করছে জানো?
So 5th April তো বলেছে।
5th April. Okay, so we have this month, right?
Yes sir.
Sir, in
Try to
fact,
get
sir, in fact,
well,
1 minus xi minus eta into 1 minus 2 xi.
uh, 1 minus twice xi.
So in fact 2 eta into 1 minus 2 xi আসছে।
So n5 is supposed to be 0 on this line, which is eta equals 0, and this line which is 1 minus xi minus eta equals 0. Is it the expression? Is it the expression that you, huh? But then you'll have to multiply with 2, right? Because at 5 the eta value is 0.5, so it is not be giving you. Acha, no, then you'll have to multiply with 4 actually. So then it is 0.5 times 0.5. Is it the correct expression?
Yes, sir.
So 4/6 এও তো 0 in 5 টা।
n5 is supposed to be 0 at 4/6. এটা তো বুঝলাম, তুমি আর কোন লাইন নিলে? 4/6 একটা লাইন নিলে
1/3।
1/3, তাহলে নোট 2 এর কি হবে?
ও আচ্ছা আচ্ছা, আচ্ছা ঠিক আছে।
একটা জিনিস খেয়াল করলে দেখতে পারবে that n4, n5 and n6, I mean I can straight away write n4 as xi, sorry, n6 as xi times 1 minus xi minus eta. Okay, simply by looking at how n5 and n4 turned out, you see with CST element the shape functions were xi, eta and 1 minus xi eta. Okay, and the shape functions for the mid side, I mean the shape functions that are unity at the mid side nodes, they also turned out to be composed of the CSTs from shape functions from the CST. Okay. So in this way we can proceed, we can do the same exercise that we did. Essentially the rest of the things remain the same. So what I'm trying to say here is since there are 6 nodes, there would be 12 degrees of freedom: u1, u2, u3, u4, u5, u6, u7, u8, u9, u10, u11, u12. Okay, so this part is pretty standard. Okay, now এই অবধি সবাই বুঝতে পেরেছো তো?
Yes, sir.
Okay.
Yes, sir.
So now you can imagine what are the following steps. So you represent u as n times u hat. Okay, then you again write n and e as n bar format, and then take gradient with respect to the natural coordinates. Then you get the Jacobian. Okay, and from the Jacobian and this gradient, you get the gradient of the shape functions with respect to the physical coordinates, and eventually construct the B matrix, and that B matrix relates to your strain through this relation. Okay, and eventually your element stiffness matrix is integration B transpose dB d bar B d omega. Now this d omega is essentially your
Thickness.
dx dy times h, which is the uniform thickness, and then that can also be written as det j times d xi d eta. Okay, which should eventually be integrated through a double integration. Okay, so this procedure is very simple and very similar. In the last class I gave you an assignment. I asked you to figure out how much was the force due to traction, the force vector due to traction coming for a 4-noded quad element. Okay, so you probably got the expression. Can you tell me, was it similar to the CST element or different?
Yes, sir. Similar, sir.
Similar. So although the shape functions were different, okay, for CST those were linear shape functions, Okay, and for four-noded quad element, they were bilinear shape functions. But the thing is, once you move to a given site, then either xi or eta is zero. Once you move to a given site, then xi or eta is zero. Then essentially the shape function becomes linear in the other coordinate, that is the eta or xi. Okay, so let's say for CST element or for this six-noded triangle element, if you move to a given site, let's say 1 2 side, okay, so then xi is zero, so eta is the only coordinate. Okay, for example, if you move to this third side, then none of the xi and eta trivially zero, but they must all satisfy the condition that 1 minus xi minus eta equals zero. So one constraint is there on xi and eta, and then if you integrate that, okay, you are going to get, in each case you are going to get the identical expression for the, I mean, because the shape function itself, shape functions on that line are linear. Okay, so you are going to get the identical expression for the force vector. So we are mostly done with what we wanted to discuss with the six-noded triangle element. But so what we should be doing now is deleting this part. But I would have been happier if I could simply clear the screen, but I cannot, because I'll have to have the Pascal's triangle for further discussion. Anyways, now let us talk about so in the last class we have seen that when and now this time I'm only drawing the natural coordinates. Okay. So these were the coordinates of the four-noded quad element. Okay, of so now if I so what we had seen, that a four-noded quad element is essentially a bar element in xi direction and multiplying a bar element. The shape functions are like that. The bar element in eta direction. So you take the shape functions like that of a linear bar element in xi direction and multiply that with the similar shape functions with the eta, and then you have the shape functions for the four-noded quad element. And then when we so that is a bilinear shape functions. So four-noded quad element is a bilinear element. Now when we move to higher order element, the quad element goes from bilinear to biquadratic. Can you tell me how many nodes would be in the biquadratic quad element? For that, you need to think of how many nodes were there in quadratic bar element.
So 6 হবে।
হ্যাঁ
8 হবে স্যার।
8 হবে? এতদিন ধরে মাথায় 8 ঢুকলো?
স্যার 6 হবে 6।
6 হবে কি করে 6 হবে আরে বাবা how did I get from 2 to 4 of course 2 to 4 can be obtained from various ways like 2 plus 2 2 times 2 2 to the power 2
স্যার 9 হবে
which
স্যার
one which one do you think has happened when I moved from one dimension to two dimension has it been plus 2 multiplication 2 or to the power 2 which one do you think has happened if I change the dimension what does happen does it go to the power or does it add up power right so because I have moved to 2 dimension okay that's why I have 4 nodes now if you are still confused if it is going to be a power think of how many nodes do you expect on a brick element 8 nodes, right? Okay, that is actually 2 to the power 3. So how do you go from 2 to 8? By taking a power, right? And this time no confusion, it's a power. So similarly, if you have 3 nodes for a quadratic bar element, you are supposed to get how many nodes for a quadratic 2D element?
3 square.
3 squared. And how much is that? 9, right? So it's a 9 noded quad element. Okay. And in Pascal's triangle, this is how it looks like. These are the terms that would contribute to 9 noded quad element. Okay. Now this is how you number them. So you can imagine this one is 5, this one is 6, this one is 7, this one is 8, and ultimately the body center or the face center is 9. Okay. Acha, this time again obeying such laws ni xi j eta j equals Kronecker delta. This time and sigma ni is 1. If I want to evaluate n1, can you tell me what should be the expression or what are the lines that I am supposed to take?
2 3 3 4
3 4. Okay, what else?
2 3
স্যার 2 3 হবে 2 3
2 3 are
6 8
6 8 are
5 7
7 5
5 7.
7
Okay,
5 7
so you see there would be 4 lines, right? 4 lines. I need to take 4 lines. Okay, there is no way I can reduce that to lesser than 4 lines. Okay, not for all shape functions at least, which means because I need to have 4 lines, therefore I'll be getting one term that is the cumulative power that has cumulative power of xi and eta to be 4. Can you see this? That's why I need this term, because ultimately I'll be, by taking 4 lines, I'm supposed to get at least one term with to the power 4, and this is the term that is going to be. Okay, so now that this is the this is the only 4th order term that you would have, that can be explained from the fact that, let me write the expression for n1. So what is the equation of line 5 7?
xi equals 0
Okay, equation of line 8 6?
eta equals 0
এটা equals
এটা equal to 0
Equation of line 2 3?
এটা equal to 1
Xi equals 1.
xi equal
xi
Equation of line 3, 4.
3, 4. Eta equal to
Eta
1.
equals 1.
Mhm. Now, if you substitute the values of xi equals -1 and eta equals -1, which are the coordinates of node number 1, okay, what value do you get for n1?
4, sir.
4. So I need to be dividing this by 4, or in other words, these are the different shape functions so this is a shape function for n1, and if you compare that to quadratic bar element, that is actually n1. So this expression is actually n1 for the quadratic bar element. Okay. Achha. So can you write down the different shape functions from for 9-noded quad element? Let's say if I have to work with one of the mid-side nodes, let's say if I have to find out n5, okay, so that is supposed to be 0 on this line, this line, this line, and this line. Again 4 lines. If I have to go for the central node number 9, so that is 0 on. So n9 is the simplest, right? n9 is basically 1 minus xi squared, 1 minus eta squared. Okay, so can you construct all the 9 shift functions for this one? Could you get all the shape functions?
করছি স্যার।
Okay.
হ্যাঁ স্যার হয়েছে স্যার।
That's it? Okay.
Yes, sir.
Okay. So next thing that you do is think of a huge mesh. Okay. Imagine I am only showing you part of the mesh. Okay. And this is how that mesh looks like. Okay. Now take one of the elements. Let's say this is the element number 1, which one has 4 nodes: 1, 2, 3, and 4. Now what is the effective node number, a node effective for this element? You see it has 4 nodes, but each of the 4 nodes are shared. Now with how many elements are these 4 nodes shared? So for a 4 noded quad element, let's say if you take node number 1, how many elements does this how many elements do share this node?
4.
Sir, 4.
4 nodes. So effectively in 1 is as much to element number 1 as to these 3 other elements, which is it belongs to node number 1 as 1/4. Okay. And if you do the same for all the other nodes, so basically you have, so this what I'm trying to get here is the ratio of number of nodes to number of elements. Okay. And that number becomes 1. And actually if you construct a huge mesh, 2D or 3D, with linear or bilinear quad element or trilinear brick element, you'd get the node number very, very close to element number. Okay. Because obviously the node number is going to be a little higher, because at the boundary there is only nodes. Okay. So node is on the either side of the boundary. So but mostly if it is a large mesh, then you would see the number of nodes and number of elements are very similar. Achha, now if I take 9-noded quad element, I'll be having node number 5, node number 6, node number 7, and node number 8. And ultimately I'll have node number 9. But let's say if I have up to node 8, okay, how are these mid-side nodes shared? How many elements are they shared with? Each of them are shared with. For example, node 5, how many elements do share node number 5?
Two elements.
2 elements. So there are 4 such nodes which are only shared by 2 elements. Okay. So now we see, sorry, I made a mistake. Now do you see that the mid-side nodes are actually costlier? Mid-side nodes are actually costlier, okay, and I'm putting within quotes, than the corner nodes. Okay, it might seem to you they are just essentially 4 extra nodes. Okay, and I have not even talked about the mid-face node. So the mid-side nodes, although they look like they are just uh, twice the number of nodes, it's not. I mean, sorry, they might seem like the exactly the same number as the corner nodes, but in a large mesh, they have twice the representation. Okay, so per element, they have twice the presence. Okay, so if you have the all I'm trying to say here, instead of taking a 4-noded quad element, if you had taken 8-noded quad element, the node count, although sorry, I made a mistake. If I have not introduced to 8-noded quad element, but in a minute I will also be introducing to you what is a 8-noded quad element. Okay, I'll talk to you about that. Okay, but let's say if there is something like a 8-noded quad element, and we can do a direct math that 8 node is actually twice that of 4 nodes. But when it comes to sharing, the corner nodes are more shared than the mid-side nodes, and effectively the node count, instead of becoming twice, it becomes thrice. Can you see this? That the mid-side nodes actually increases your node count or mesh count. Okay, or for a given number of elements, the node count becomes not twice but thrice if you have the mid-side nodes. এটা বোঝা যাচ্ছে কি কি বলতে চাইছি?
রিপিট করুন স্যার।
মানে our understanding of 4 versus 8, okay, if we could construct an 8-noded quad element, okay, immediately our mind would be thinking that our mind would be thinking that the node count, okay, keeping the number of elements same, the node count would simply be twice. Okay, because 8 is twice of 4, but that is not the fact here. Okay, if you do a really large mesh, because the mid-side nodes are only shared between 2 elements, each of the mid-side nodes are only shared between 2 elements, the node count doesn't increase by twice, it actually increases by thrice. That is, this is the quantity that I'm writing, number of nodes per element. Okay, in a large mesh, for a 4-noded quad element, the number of nodes per element is 1. For 8-noded quad element, that becomes 3. So from 1 it goes to 3. এটা বোঝা যাচ্ছে কি হচ্ছে? বোঝা যাচ্ছে? আচ্ছা, now think of the 9-noded quad element. Let's put the central node number 9. How many element is this 9th node shared with? 1. So basically you need to simply add 1. I mean, in your mind, in a 9-noded quad element, okay, what is the node count, change in node count? Why am I bothered about node count? Because you see there are 2 degrees of freedom per node. Okay, and the number of nodes, number of degrees of freedom is proportional to number of nodes, total number of nodes, not per element. Okay, or that is total number of degrees of freedom. And actually your global stiffness matrix, the size of that is NDOF times NDOF. That means that is the number of equations you are supposed to solve. NDOF number of supposed equations you are solved, either for the degree of freedom or for the reaction force. Okay, so that would be your computational task. Okay, and that much computational time would be required to solve a given problem, and that computational time is the cost for a given problem. Okay, and as you can see, once I go from 4 node to 8 node, that task doesn't increase by twice but by 3 folds. Okay, now in your mind you would be thinking going from 8 to 9 is only 1.125 times, right? That is 12.5% is the increase in the task going from 8 to 9. But think about this, how much is the increase going from 3 to 4? It's actually this much increased task. The last node is the costliest. বুঝতে পারছো কি বলছি?
Yes, sir.
মানে একটা আমাকে যে সিস্টেম ম্যাট্রিক্স সলভ করতে হবে, আমাকে যে সেট অফ ইকুয়েশন সলভ করতে হবে, দ্যাট ইজ অ্যাকচুয়ালি NDOF number, মানে যতগুলো ডিগ্রি অফ ফ্রিডম আছে টোটাল গ্লোবালি, and that number is actually proportional to the total number of nodes, and that is basically number of elements times number of nodes per element. Okay, effective number of nodes per element. এবার এই যে effective নাম্বারটা, okay, while going from 4 to 8 it changed from not twice, it changed to not twice but thrice. And while going from 8 to 9 it didn't change by 12.5%, it changed by 33.3%. Okay, so we can see that this 9th node is very costly, because obviously because it is not shared with anyone. So what we can think of is getting rid of that node. In terms of polynomials that contribute to the shape function, we would get sorry, I should be choosing a different color. Okay, so this is for 9q. Let's take blue. So up to this is for 8q, 8 noded quad element. Now why I gave up this term xi square eta squared term? There are a few reasons. Number one, let's say, is that I'm supposed to only give up a symmetric term. That means I should not be partial with xi or eta. I can only get rid of terms that have the equal powers of xi and eta. So that qualifies 3 terms: 1 xi eta and xi square eta square. Then comes the number 2 point. The first law of getting shape functions, the shape functions must be complete. Okay, I mean it can be linear, it can be quadratic, it can be cubic, but when it is cubic it is not giving up the quadratic terms, and when it is quadratic it is not giving up linear term, and when it is linear it is not giving up the constant term. Because let's say y equals c0, even this is a linear equation. Okay, it is like c0 plus c1x, is just that c1 is 0, and it is also, and any equation which is like c0 plus c1x, also a quadratic equation, is just that c2 is 0, and so on. You can think in this way. So when you are getting a given order of the polynomial, you need to also accommodate all the polynomials which are lower than that. Okay, that is a basic rule of getting shape functions. That way the shape functions are complete. Okay, so you can always get rid of the highest power but not the lowest power. So this term over here qualifies for both. it is symmetric, and it is also the highest power. That is why you'd get rid of this term. Okay. Now imagine if the 9th node is not there. But before going into the shape function of 8-noded quad element, this 8-noded quad element has a name, and that name is the serendipity element. I may be wrong with the spelling. Okay, you need to check TY obviously, but I'm not sure whether it is TE, DE or DI. So serendipity element. What is the meaning of the term serendipity? I don't understand much of it, but it is mostly like getting extra out of lower cost. Okay, it is some sort of meaning like that. Okay, so you are actually getting eventually quadratic terms, xi squared and eta squared terms. So basically your shape functions are still some way quadratic. Okay, but you get to use 25%, that is 3/4 is 0.75, and this thing I wrote 4/3. So you get to use quadratic shape functions, in some sense quadratic, okay, with 25% lesser number of nodes. It's kind of like 25% discount. Okay, hence the term serendipity. Okay, but obviously in mathematics there is no free lunch, and you also pay the price for getting quadratic shape functions at 25% lesser number of nodes. Okay, so there is issues called overshoot and undershoot. Okay, Achha, by the way, if you go to any finite element software, ANSYS, Abacus, Nastran, Patron, all the commercial softwares, they use this serendipity element. Why do they use this serendipity element? Because they are competitive. They are competitive with one another. Okay, and they cannot afford to have higher calculation time. Okay, then they would be, that software would be immediately discarded. I mean, you might be thinking that why does it matter? Why does the cost of computation matter? But imagine in an industry, if you are running a finite element simulation, you probably have 1,000,000 degrees of freedom. Let's say 1,000,000 number of nodes. Then for a 3D simulation, there is 3,000,000 degrees of freedom. Okay, and that probably takes over a week for a single simulation. Okay, and in that week, if you increase 33% higher cost, okay, so that becomes around 9 to 10 days. Okay, 2 or 3 more days, which could be extremely costly if you are running multiple such simulation. Okay, let's say for a design purpose, you have to run 10 such simulations. Okay, so then you are probably be missing your deadline. Let's say if you are to complete a task within a month or couple of months, you would be late by 10 days. So only because of simulation. Okay, so that can be very challenging, and people don't want that. Okay, and because people also do not understand what is the underlying mathematics behind such scenarios. Okay, people would obviously go for one that gives you lesser number of nodes, lesser number of degrees of freedom, faster solution. এই পার্টগুলো কি বোঝা যাচ্ছে কি বলতে চাইছি?
Yes, sir.
Yes, sir.
So if you look at any commercial software, they use the serendipity elements, but these serendipity elements have different problems. Typically, if you work with let's say conduction problem, thermal or electrical conduction problem, if you use the serendipity element for conduction problem, you end up having something called overshoot and undershoot. And undershoot. What do I mean by that? So I have some personal experience with using them for conduction problems. Okay, so imagine there is a block, simple block, okay, maybe of multiple layers of metal, different metals, okay, a composite maybe. So to one end you applied a temperature of, let's say, 300 degrees Celsius. Okay, at the other end you applied a temperature of, let's say, 50 degrees Celsius. In a simple conduction problem like this, nowhere in the geometry the temperature should go below 50 degrees Celsius or go above 300 degrees Celsius. With serendipity elements, you can have solution. You can have solution where you end up having overshoot and undershoot. That is temperatures below 50 degrees Celsius and temperatures above 300 degrees Celsius within the geometry. Okay, and the simple solution to that is to go from quadratic element to simply the linear element. Okay, uh, simply go for the linear element. Okay, simply switching to 4-noded quad element would solve this problem. Okay, or for that matter 8-noded brick element would solve this problem. And and the problem is many of these finite element softwares, the default at least in ANSYS I guess, the default option is to go with the serendipity element. Okay, and actually if you move to 3D, the serendipity element kind of becomes obvious, because then you work with 20 node brick element. Okay, so that 20 node only appear at the corners. So 8-node brick element would be the trilinear element. Okay, so in 3D the number of nodes that you can get, okay, first of all effective number of nodes, first of all 1 coming from the all the corner nodes, then for all the mid-side nodes, okay, and there would be how many elements, how many sides are there? There are 12 sides, so there will be 12 such nodes. So it is a 20-node brick element. Okay, now these mid-side nodes are only shared with 4 elements. Okay, one that sits top of it, one that sits in front, and one that sits, let's say this node would be shared with the element that sits top of this element on this surface, one that sits in front of the element, that is this surface, and one that sits top of the element that sits in front. Okay, so it would be shared with 4 nodes, so 12 by 4. Okay, so there would be effectively 4 nodes. Okay, 4 times the computational cost, with once you move from 8-noded brick to 20-noded brick, 20-noded serendipity element. Then if you include the face nodes, which none of the softwares do, now there are 6 faces. Okay, and each face node would be shared with 2 elements. So you have 6 by 2. And then if you include the body center, okay, that is not shared with anyone. So you can see that if you wanted to go with the consistent formulation, okay, with the Pascal's triangle or Pascal's pyramid for that matter, if you wanted to be consistent with Pascal's pyramid, then to have a 27 node brick element, okay, you must have, for a large mesh, even for a large mesh, you must have 8 nodes per element. But with serendipity element, you have 4 nodes per element. So that 33% saving that we are talking about, okay, that has now become 100% saving. Okay, or the 25% saving that we are talking about, okay, that has become 50% saving, which is a quite a lot of saving in computational time. And that's why if you give me a choice between 27 node and 20 node, I'll obviously be going for 20 node if I do not know the underlying mathematics of it. So the use of 27 node brick element you will only find in academic institutes where people are doing research and they are writing their own finite element programs. In finite element softwares you will not find this. Acha. So now let us go back to the discussion of 8-noded brick element. Okay, and I'll simply delete everything that is. Acha, no, I'll have to have the Pascal's triangle. So I'll just erase few of the stuffs. Now with 8-noded brick element, it becomes a challenge. How do you construct the shape functions? Okay. Now let's see, if I tell you we are still obeying that condition, ni xi j eta j is delta ij, and sigma ni equals 1. Okay, so in this case 8 of those are there. So now if I want to construct, let's say, the shape function for the first node. Okay, so you see that the highest order of the terms are cubic, which means I can take only up to 3 straight lines. The highest power, cumulative power of xi and eta is 3. Can you see that?
Yes, sir.
So the maximum number of straight lines that I can use to construct a shape function is 3. So let's say if I want to construct n1, which would be unity at node 1, everywhere else it is 0, what would be the straight lines that I must look into?
2, 3.
2, 3, okay.
3, 4.
3, 4 and
2, 4.
2, 4. 2, 4 ki jonne? By taking 2, 3 and 3, 4, you have already made it 0 on 2 and 4. Just understand that there is no node number 9 now. Okay, at the center there is no node. You are not supposed to make it 0 at the center. You are not required to. So what you would be doing is you would be taking line 2, 3, line 3, 4, and then taking line 8, 5. So you see, equation of the line 2, 3 is xi equals 1 or 1 minus xi. 3, 4 is 1 minus eta. And 8, 5, what is the equation of line 8, 5?
1 plus eta plus eta.
Okay. Now if you substitute the values xi equals -1, eta equals -1, what value do you get?
-4.
So you divide this whole thing by -4, and that's when you get your shape function. Okay. Now let's see if I so you can now figure out what are n2, n3 and n4. Okay, but can you tell me what is n5? How do you get the n5? What are the straight lines that you are supposed to take?
So 2, 3,
3,
2,
4.
3, 3, 4,
3, 4,
4, 1,
1, 4.
1, 4. So all the nodes would be covered other than 5. Okay, so try to get the shape functions for n1 to n8. And because you are taking only 3 straight lines, you are never going to get anything higher than to the power 3, I mean cumulative power. Okay, and you will also not be encountering any xi cube or eta cube. It's because at least one of the terms from for each natural coordinate there should be one of the terms, like 1 minus I or 1 minus eta, like that. আজকে আর কিছু আমরা পড়বো না, তো সাম জাস্ট ending the recording.